But what does attention actually look like? I mean, if some keys contribute more than others to a given query, wouldn't it be great if we could visualize that? That way, we'd gain more intuition about what the model has actually learned. And that's exactly where we're heading next, into the attention visualizations. To do that, we first need to recall that these 300 queries and 300 keys correspond to a single area of 300 spatial positions. Again, the attention weights represent how each of these 300 positions attends to all the others. Now, even though we've computed attention for each area in isolation, we know that all 4 areas are needed to reconstruct the full spatial representation for a single attention head, covering a total of 1,200 spatial positions, arranged as 30 in height and 40 in width. So, what we're showing here is exactly that, a 30 by 40 grid, which gives us 1,200 positions, divided into 4 areas of 300 positions each. Since 300 isn't a multiple of 40, it creates a visible step here. Area attention is without a doubt the core innovation of YOLO12. For example, when we run inference on this image and apply attention, unlike YOLO11, which attends to the entire feature map, YOLO12 breaks attention into distinct areas that operate independently. This enables the model to apply attention over higher resolution feature maps. Now, let me start by playing this. It might look a bit chaotic at first, but I'll explain what we're seeing. Here, I'm showing the attention weights for each of the 300 queries from Head 1, Area 1. You can see the query number in the left menu bar and also at the top. This top area of the image doesn't contain much relevant information, so it's no surprise that we don't see anything meaningful here, just a scattered set of values with no clearly recognizable patterns. And the same happens when we visualize the 300 queries for Area 2. Although toward the last few queries in this area, we start to catch the faint outline of what seems to be the car. To keep things complete, we'll go ahead and show the key values for each of the queries in this area, right up to query 600, so you can get a full picture of how attention behaves across the entire region. But things get more interesting in Area 3, where most of the car is actually located. Here we see certain queries paying strong attention to specific keys that outline the car's contours and body. That's the dominant theme in this area. We can clearly see that the queries inside the car body pay attention to keys that are also within the car. This shows that the model is recognizing patterns that belong together, treating the car as a unified structure. Additionally, toward the end, some queries even focus on more specific parts of the car, such as the wheels, clearly highlighting meaningful structures the model has learned to recognize. This kind of focused attention is important because it reveals which parts of the image the model considers most relevant when making decisions. By observing which regions light up in response to each query, we get a window into the model's reasoning process, how it associates different parts of the image to form a coherent understanding. And that in turn helps us interpret and trust what it's learning. It's worth noting that unlike convolutions, which are limited to local neighborhoods, attention allows for these long-range dependencies to be captured directly across the entire image. And remember, this is just one attention head. The other head may focus on completely different aspects, like textures, boundaries, or background elements, helping the model build a layered understanding of the scene. And one last thing I'd like you to keep in mind is that this pattern isn't hard-coded. The model dynamically learns to focus based on the actual image content. So in another scene, these same queries might attend to entirely different regions. And that brings us to the final query representation for this area. For completeness, we'll also show how the queries in Area 4 attend to each of the 300 keys. However, since there are no prominent objects present in this region, we don't expect to see any meaningful patterns emerge. And that's a wrap on our attention visualizations, a fascinating window into how the model actually learns to focus. These patterns aren't fixed, they emerge because during training, the model learned to associate certain queries with meaningful visual features, letting it adapt its focus dynamically from one scene to the next. With that, we're ready to return to the attention weights matrix for a single area. While the queries to keys view is technically correct, since it shows attention from the query's perspective, we now need to transpose it. This transposition doesn't alter the attention weights themselves, but it rearranges the layout so that we can properly carry out the matrix multiplication with the value matrix, which we'll see in just a moment. We know the value matrix for a single head and area is 32 by 300, and it contains the actual content or visual information that, when weighted by the attention scores, produces the output that is passed along. These values contain the relevant features extracted from the input data, which the model uses to make informed decisions. Then, the attention weights calculated earlier are used to compute a weighted sum of the values, where each value is weighted according to its corresponding attention score. Therefore, the attention output is the weighted sum of the values, reflecting the similarity between the queries and keys. This gives us the attention matrix, having followed all the steps in the attention formula. And with this, we've completed the scaled dot product attention. That is, the attention computations for our input feature maps. While we have mostly walked through the matrix operations for a single head and area, these operations are performed simultaneously for all. Therefore, our 32 by 300 tensor is technically a 4-dimensional tensor, with shape 4 by 2 by 32 by 300, representing the 4 areas and 2 heads. Since our tensor already contains both heads, it's equivalent to having been concatenated along the head dimension. So this effectively corresponds to the concatenation step you see here. We are now here, and we can display the resulting attention tensor. However, to proceed with the next operations, we need not just this tensor, but also the value tensor, the same one we used earlier during the attention computations. This time, though, we'll reuse it for a different purpose, as you'll see shortly. Let's place both tensors side by side. You'll notice that they share the same dimensions, though of course their values are different. To match the code, we'll adopt the same naming convention, where the attention tensor is now stored in the variable x. Before we can work with these two tensors, we need to apply a few transformations. Fortunately, the same operations are applied to both tensors, so we can walk through them together. First, we permute the tensors to change the order of their dimensions. In PyTorch, permute reorders the dimensions of a tensor without changing the underlying data, just how it's arranged across axes. Next, since our area is greater than 1, as shown in the code, we reshape the tensor to 1 by 1200 by 64. This prepares it for another reshape, which arranges the values into a 30 by 40 spatial layout. Finally, we apply one more permute, which reorganizes the dimensions into the format you see here: batch, channels, height, and width. We now have both tensors in the correct shape and format for the next step. And in particular, we'll focus on the reshaped value tensor to apply what's known as positional encoding.